Hey there, and welcome. Every single day we put this incredible trust in the food we eat. But have you ever really stopped to think about how we know it's safe? Well, today we're going to pull back the curtain on this amazing global quest to keep our food safe, right down to the microscopic level. Let's dive in.
Right? It's a huge question. And the answer, well, it involves this massive coordinated effort by scientists all around the world. And they're tackling a challenge that most of us never even see.
Look, to feed billions of people, farmers often have to protect their crops from pests. And sometimes that can leave behind these tiny, invisible traces called residues. So the big challenge is to make sure those amounts are so incredibly small that they pose absolutely no risk to our health. So who are the investigators on this case? To solve an invisible challenge like this, you need a special kind of detective. We're talking about a dedicated, international team of scientific experts. They operate completely independently, with just one mission in mind.
They're called the JMPR. That's the Joint FAO/WHO Meeting on Pesticide Residues. Just think of them as the world's food safety detectives. They're not tied to any single country or any company. Their one and only job is to look at all the science, all the data, and figure out what is safe. And I do this with some seriously precise science.
So how in the world do you figure out what's safe? Well, it all starts in the laboratory with one fundamental question. At what point does a substance actually cause harm? The answer to that question is the starting point for everything else. It all comes down to a concept called the NOAL. That stands for No Observed Adverse Effect Level. Scientists figure this out through tons of studies where they find the absolute highest dose that causes zero detectable harm. You can think of it as the tipping point. It becomes the bedrock, the foundation for every single safety calculation that comes next. Now, from that NOAL, scientists get to something called the ADI, or Acceptable Daily Intake. And how they do it is pretty brilliant. They take the NOEL and they divide it by a huge safety factor, usually at least 100. This creates this massive buffer to account for any differences between lab animals and us, and even between different people. The result is the ADI, your personal daily safety budget. It's the amount you could literally have every single day for your entire life with no health risk.
And to make this real, here's an example. The ADI for a fungicide called carfentrazone ethyl is just 0.03 milligrams per kilogram of body weight per day. It's a super tiny number, yeah, but it's built on a mountain of data and a huge safety margin. But a safe dose in a lab is only half the story. The real question is, how does this all connect to the food that's actually grown on a farm?
Okay, so knowing the safe dose is one thing, but what actually happens to these chemicals out in the real world? The JMPR detectives have to investigate the entire journey, right from the moment a pesticide is used in a field. And their process is so logical. It all starts with those toxicology studies we just talked about to figure out a safe dose. Then the investigation moves into metabolism. How do plants and animals actually break the chemical down? Then it's out into the real world for field trials to measure what's actually left on the crops. And only then can they combine everything to assess the real risk to our diets. And when I say thorough, I mean wow. They look at how a chemical is broken down in livestock, like how fenpropidin is metabolized in goats. They measure the exact residue levels on crops, like for azoxystrobin on melons. And get this, they even study how the chemical behaves in the soil and whether it could be picked up by the next crop planted in that same field. It's the whole shebang. Okay, so now the detectives have all this data from the lab and the farm. The next crucial step is connecting all that science to what people like you and me actually eat, right? I mean, someone who eats a ton of apples is going to have a different exposure than someone who barely touches them. And this is where you can really see the science evolving. The older models use these really broad diet estimates, like a general European diet, which was okay, but not super specific. The new models, though, like the GECD, are way more powerful. They use detailed data from individual countries. This lets scientists check the risk for specific groups, like toddlers, and even for those of us who eat a lot of one particular food. So, the investigation is complete. All the evidence is in, from the lab tests, the field trials, to the dietary patterns from all across the globe. Now, it's time for the verdict. And all of this work, this massive global scientific effort, it all funnels down to a single critical number for each pesticide on each food. And that number, it becomes the global standard. It's called the MRL, or Maximum Residue Limit. And the best way to think about it is like a legal speed limit for a pesticide on your food. It's not the danger level, not even close. It's a legal line drawn way, way below any health concern. MRLs are set so that even if you ate food with residues at the absolute legal limit, your total intake would still be safely inside your personal daily budget, that ADI. And just look at how specific these limits are. For example, the MRL for a fungicide on melons might be 5 milligrams per kilogram, but for an insecticide on sugar beet, it could be 1,000 times lower, at just 0.004. Each number is tailor-made, a unique verdict based on the science for that specific chemical on that specific crop.
So the standards are set. Our food is safe. Case closed, right? Well, not exactly. In the world of food safety, the case is never really closed.
Because science never stops. As new methods are developed and we get more data, the JMPR is constantly reevaluating things. For instance, right now they're doing this huge reevaluation of a whole group of fungicides called dithiocarbamates. It's a cycle of constant vigilance, always improving. So the next time you pick up an apple or a melon, you'll know the answer to our big question. You'll know about this invisible global system of scientific detectives working around the clock to keep it safe. And that really just leaves us with one last thought. As our world keeps changing, how will this amazing system continue to evolve to protect our food in the future?